Hello, physics students. So in the last topic, we learned that a current was electrons flowing in a wire. And then in this topic, we learned that if electrons move through a magnetic field in the right orientation, a magnetic force is created. So it follows that if we've got a current carrying wire in a magnetic field, that creates force on the wire. And that's the topic for today. Magnetic force on a wire. Now, when it comes to determining the magnetic force, we need an equation for the magnitude and we need the right-hand rule for the direction. Remember, there are two right-hand rules. This one is to help us find the direction of the magnetic field around a wire. This one is to help us find the direction of the force. This is the one we need, right-hand rule number 2 today. So what I want to do is begin by you practicing this right-hand rule to figure out the direction of the force on this wire. Now remember from circuits that if the current is flowing this way, what's really happening are the electrons are going this way in the wire, from right to left. So there's an electron velocity this way. What I want you to do, I'm going to create a pause, use this right-hand rule to figure out the direction of the force. So go ahead and do that now. All right, well, hopefully you did it. Again, don't just watch passively. Do these practice problems. It's okay if you're at home watching. If you get it wrong, no one's even going to know, but you should be practicing. So velocity is this finger in the direction of the velocity. I put my index finger. Next, I have to turn my wrist so these 3 fingers point in the direction of the magnetic field. So I turn like this. Right? I can't do something like this. I got to keep my index finger going that way. Turn, turn, turn. There. I have my 3 fingers pointed in the direction of the magnetic field. My thumb points into the board. That would be the direction of the force if these were protons. Since they're electrons moving that way, the force is in the opposite way. So I'll draw an arrow out of the board like this, and there is the force. Okay? We could even put a little vector symbol over it. Now, what I want to show you is that you don't have to do the right-hand rule on the electrons moving this way. For today, you can assume that in a current-carrying wire, there are actually protons flowing this way in the direction of the current. If you do the right-hand rule with protons moving in the direction of current, you get the same answer. What I want to do is create a pause now to allow you to repeat the right-hand rule for positive charges moving this way with the same magnetic field. So go ahead and practice now. All right, so this is what you should have done. You should have put your index finger going toward the right of the screen like this. Then you have to turn your wrist so your 3 fingers point in the direction of the magnetic field, as they are right here. And you see my thumb points out of the board. So for today, you can always just use current like this with a right-hand rule. Not always true with magnetism. There'll be a future topic called the Hall effect. I'll explain where you actually have to do the right-hand rule with electrons. You do it with positives moving for current and you get the wrong answer. But today, it's okay. Just do velocity like this. All right, that's the direction. The magnitude. You could use the cross product, the magnitude of the current times length L as a vector, the length of the wire, in meters, of course, cross the magnetic field, or you could just do ILB sine theta and the right-hand rule number 2. So let me create a pause to allow you to catch up with the notes if you need it. All right, what I'm going to do next is I'm going to send you back in time to our classroom. A few days ago, filmed some demonstrations with a wire carrying current in what's called a horseshoe magnet. So let me send you back there. Again, you're going back to practice the right-hand rule. Well, to see the effect it really actually happen, but also to practice right-hand rule. Don't just watch and wait for the answer. Practice and see if you get the right answer. So here you go. What we have here is a power supply, a coil of wire, and what we call a horseshoe magnet. A horseshoe magnet is essentially a bar magnet that's been bent into the shape of a horseshoe. That means it also has a north and south pole. You probably can't see it on the screen, but on this end, it's marked with a little n and this an S. So this has magnetic field that goes from this side to this side, pointing in your perspective from the left side to the right. There's a B going this way. Now, this horseshoe magnet is very strong. To demonstrate how strong, I have here just a piece of iron, and I'm going to bring it near the horseshoe magnet. And you hear that tremendous violence of that attraction. If I had my hand in between, it might even cut it. And in fact, I could lift this whole heavy horseshoe magnet by the strength of that attraction. I got to pull it apart to separate them. So I'm going to pass a current through this wire. And as you know from the circuit topic, a current consists of electrons moving through a wire. And in this topic, we learned in the previous video, electrons moving through a wire create, in a magnetic field, or electrons moving through a magnetic field create magnetic force. The first thing I'm going to do is pass the current with this side being positive. And what it's going to do is come through this wire and go into this side of the coil and go around. And now the wire here loops around multiple times to increase the magnetic effect. So this is going like this. In other words, inside the horseshoe magnet, the current is going away from you. What I want you to do is, in the pause, figure out the direction of the force on this coil of wire using your right-hand rule for force. Again, currents pointing this way into the, or away from you, and the magnetic field points that way. So go ahead and use the right-hand rule to determine the force. All right, so current is considered positive charge moving this way. So we have velocity going in, like this. Maybe I'll turn this like this, velocity going in. The magnetic field goes from north to south, so my hand is the wrong way. I've got to turn it over. Oh, yeah, I got to move over here like this. And I see that the force on the wire is in the downward direction. So if I flip this on, you'll see nothing happened because that wire is just pulled downward. You might be able to see a little twitch of it pulled down. So nothing dramatic. So what I'm going to do is now turn this around. Now obviously the force is up now, but let's see if you could practice that. So go ahead and use the right-hand rule. Now the current is going to go in this side, go around the back here, and go through this bar magnet in this direction. The magnetic field points this way. So go ahead and use the right-hand rule to figure out the direction of the force. So let me show you that it does indeed come out upward. Current is this way. The magnetic field goes from north to south, left to right, and you see my thumb is pointed upward. I'm going to turn the power supply on, and we'll see evidence of that force. Whoa, dramatic, right? So let's see that again. Oops, wrong way. So here it goes. Ready, set, go. Flew right out of the magnet with tremendous velocity and acceleration, I should say. Now, one of the things that this proves, besides that there is a magnetic force in a current-carrying wire and that the right-hand rule works with current, magnetic field, force, is just how strong this magnetic force is. Because what's pulling this down is the force of gravity. What does it take to create this amount of gravity? The entire planet Earth. That means the molten core, Mount Everest, the Indian Ocean, the Pacific Ocean, Australia, Europe, all of that mass of the Earth, the entire mass of the Earth, and it pulls down with a force of gravity like that. Squared against that is one dinky power supply. This is fighting the entire Earth, this magnet and this power supply. And guess what wins in dramatic fashion? The power supply. Why? It's creating a magnetic force. not even a billion, not even a trillion, way stronger than the gravitational force in nature. So another interesting thing. Okay, so back again. So the next thing we're going to do is calculate the torque on a loop of wire. This is essentially the phenomenon of how an electric motor works, and there'll be more about that later. So what do I mean by a loop of wire? Well, here's just a scrap of wire I have from some of the circuits I'm working on in my house. So it's like a rectangle of wire like this. We're going to have current going one direction or another. So there it is. Example, determine the torque on this loop. And remember, torque in physics is like a turning force. So like if on a steering wheel, here's the radius, you've got to push perpendicular, you make this turn. So that's what we're trying to find, the turning force, the torque on this wire loop. It's got current going around in the counterclockwise direction in a magnetic field pointing to the left within the board. And here are the dimensions, 0.2 by 0.3 meters. There's 2 amps of current and half a Tesla of magnetic field going like this in the board. So first thing we have to do is find where there's force, so we could start thinking about torque, which is RF sine theta. So along the top and bottom, the magnetic force is 0. Why is it 0? Because this magnetic field and the current are at an angle of 0 degrees apart. You plug in 0 here, ILB sine 0, you get 0 newtons on the top and bottom. Not 0 on the sides. So what we have to do is figure out the magnetic force. Let's begin by figuring out the magnetic force on this side. I'll create a pause. You do it. Don't wait for me. Practice and see if you could figure out the magnetic force. So, go. All right, well, this is what you should have done. You should have put your index finger in the direction of the current like this. And oh, my hand's already set up like that. Look, magnetic field going this way, and my thumb is pointing out of the board. So the force here is straight out of the board. So that looks like this. Okay, there's the force on the right side of the hoop. Now, repeat the right-hand rule for this side. Go ahead and do it in this pause now. Go ahead and figure out from the right-hand rule. All right, this is what you should have done. You should have said, okay, this is going to be a little tricky for me because it's up high. So I have the current going like this, down, and then I have to turn these 3 fingers so they point in the direction of the magnetic field without changing my index finger. So I'm just going to move my whole body like this over here, and I see that I have current, magnetic field, and so my thumb is pointing into the board here. On this side, the force is into the board, so let me add that force. Okay, so I can find the magnitude of those 2 forces. They're the same because it's the same current, the same length, and the same angle of 90 degrees to the magnetic field. ILB sine 90, length being 0.3. 90 degrees, again, because magnetic field's like this and the current is like that, so they're 90 degrees to each other in both places. So that gives me 0.3 newtons. So if you need a moment, I'll create a pause to allow you to copy this down. All right, moving on. 0.3 newtons. Now I need to find the torque. And basically, if I have this wire loop, if I lift this like this, while at the same time pushing this in like this, I'm creating a torque on both sides that adds. So if I were to take this and turn it like this, this is that view with current here going in, coming out. I'm pulling up and pulling down. That's going to create the same kind of amount of torque. So the net torque will be the torque here plus the torque over there because they're both counterclockwise. I'm adding them. Remember again, torque is RF sine theta, RF sine theta. But here's the thing. This is a different theta. The original theta, okay, they both end up being 90 degrees. But I just want to point out it's a different theta. It's measured in a different place even though we get the same answer of 90 degrees. The first theta was between current and magnetic field. This theta is between, because it's a torque calculation, between the force and the radius. In other words, it is right here. This is theta 2. Okay? So I plug in, since these torques are the same, I'm just going to calculate one of them and double it. Where is the radius? The radius is how far away the force is applied to what we consider our axle. So this is the radius right here. And it's the same for both sides. It's 0.1 meters because this is 0.2 meters. So RF sine theta 2, and there's 2 torques, gives me 0.06 meters, okay? Now, a thing I want to point out is that this torque is a maximum in this particular situation. So we've got these forces. One is down and the other one is up. Okay, so this creates maximum torque because these markers are the force 90 degrees from the radius. But as this turns, see what happens? The angle, well, I'll hold it right here. The angle between the force and the radius over here is no longer 90. So this is 90 degrees maximum torque. And then what happens? We get less and less torque until we get to here where we have 0 torque, because the angle between the radius and the force is, well, you could say 0, 180, doesn't matter. That gives you 0 torque. So the torque is a function of what angle this hoop finds itself in. And that's what that graph is showing, maximum 0.06 or negative 0.06. And, but the entire time, theta 1 in this calculation, the current, no matter how I change this angle of this hoop, the current and the magnetic field, current and magnetic field here are always 90 degrees to each other. And so the forces are always 0.3. The torque is only changing because this angle is changing. So that's an example of something you might have to do on an AP test, calculating your torque on a hoop. Let me create a pause to allow you to catch up. Okay, I have another demonstration in the classroom I want to send you to look at. In this demonstration, I show the basic principle of how torque on a loop can be utilized in a device to create continuous torque. In other words, to make an electric motor. Okay, so let me send you back to that moment. So enjoy the demonstration of how an electric motor works. What I'm going to demonstrate is that the magnetic force on wires can create a torque. Remember, in mechanics, torque was mathematically defined as RF sine theta, but in conceptual terms, it's like a turning force. Like, for example, when you turn your steering wheel, you create a torque by, here's the radius to the axle of your steering column, and you pull up and the wheel turns. So a turning force. And so I'm going to take that same wire, and then rather than have it like this with one side out of the magnet and one in, I'm going to put them both sides into the magnetic field. And so now if I see the current is coming and going out this way on this side and in this way on this side that's over here. So this way out here and this way in here. So that is in the presence of the magnetic field from north to south. So for the current that's going this way, then we can use the right-hand rule and see that the force on this is current. Now my 3 fingers have to be turned to go toward the south pole, and the force is down on this part over here. On this part in the front, the current is now coming straight this way. And so I could do, for this part, current, magnetic field, and the force on this part is in the upward direction versus this one. So this side is going to be pulled up, and this side is going to be pulled down when I turn the power supply on. So what I can do is basically turn this 90 degrees. You see it snaps sort of to attention like that because it's like I'm pulling up here and pushing down here, and it goes like this. And then the pull and the pushes then freeze it in the vertical direction. So that was, maybe it'll be clear like this if I show you, right? It flips up like that. Now it's stuck in that sort of stuck upward position. But if I could flip the current around, so instead of it going this way and creating a force up here. On this top wire, it's going to go here and create a force down. If I could flip that by just switching these wires, you'll see that I can now create a 180-degree flip of this wire. There it is, right? So it was like this, and now it's stuck like this. Now it's stuck like this. What if I flipped the current again? So instead of this wire being pulled down, this one up, it's going to switch, this one pulled down and that one pulled up. Well, let's do it again. You probably know already, but let's just see it in action. And here we go. Turn it on and it flips again 180 degrees. And if I keep switching the wires over here, I'll get a 180-degree flip, switch the wires, another 180-degree flip, switch the wires, get another 180-degree flip, and look at what I'm doing. I'm creating a continuous rotation. And that would be essentially a very crude, impractical electric motor that would then, every 180 degrees I'd have to flip the wires. There is a very ingenious invention, though, to create that flipping automatically. So I'm going to reconfigure the camera and show you how. What I have here is a device that's essentially a very crude electric motor. It's not designed to do any useful work other than to spin and show you the principles that work in an electric motor. Now, as we saw in the previous demonstration, if I keep switching the direction of the electricity in coils, I get the coil to flip in the horseshoe magnet 180 degrees over and over again. So this doesn't cause the flipping by switching these wires manually up here. It utilizes what are called brushes. So I have my magnetic field here. This is the south end of the magnet. This is the north end. The magnetic field goes like this, and I got a couple coils. Now if I turn this and hold this like this, you can see that this coil touched by my finger is right now connected this side to the positive wire through this brush, goes up here, and so I've connected to this part on my finger to positive. As the motor spins, you see that now this metal plate on this axle loses contact with the positive and comes around and touches the negative brush over here. And what used to be on the negative side over here has now come around and touched the positive. So as this spins, the brushes automatically change the direction of the current continuously. So now what I'm going to do is put this here and pass an electric current through that coil, and we'll see that the brushes allow the coil to flip continuously and spin the motor. So let me crank up the volts. Sometimes it needs a little start, and you see, there it is, okay? Spinning through the changing of the direction of the brushes. Shut off the current, and it winds down. Really simple, but very clever device. Humans are so clever figuring out how to use these magnetic properties to practical ends. Okay, so the electric motor tied everything we've learned together so far. There are electrical forces creating current. The current is creating magnetic forces. So it truly is an electromagnetic device. Very powerful device, very useful device, very beautiful device. All right, one last thing for today. We have to figure out, you have to be able to figure out the force between two wires that are distance apart. And it goes without saying there has to be current in these two wires. So here's case one, cross section where the wires are coming out of the board, the current's coming out of the board straight at your eye. So what we have to do is figure out, are these wires attracted to each other or repelled for the various situations. One case, they have the currents in the same direction, and then in the other case, the currents going in the opposite direction. So this is now going to involve both right-hand rules. We need this one, right-hand rule number 1, and right-hand rule number 2. The first question I'm going to ask you is, what is the magnetic field caused by this wire at the location of this wire? So I'm going to create a little pause, figure it out. Again, don't wait for the answer. Give it a shot. So here's the pause. All right, so you should know that the magnetic field is going to go either this way around a wire or this way. And that's why we use our right hand rule number 1. We put our thumb in the direction of the current, and then it tells us our 4 fingers naturally bend in the direction that the magnetic field goes around this wire. So arrows like this, like this, like this, like this, and right here, straight up. So this is the magnetic field caused by wire 1. I'm going to put B1. Okay, now that's going to create a force on this wire. What I'm going to do is create a pause to allow you to figure out the direction of the magnetic force on wire 2. So go ahead and do that now. All right, you should have been doing this, and you should put your index finger in the direction of the current, which is out of the board, and then these 3 fingers have to align with the magnetic field while holding this direction constant. So I'm going to swivel my wrist like this, and now I have my hand in the right position. This is the force on the wire going inward, directed inward. So that is, maybe I'll do it in blue, like this. The force on 2. I'll just put F2. This is a diagram, get too cluttered. Now, what's the force on this wire? You could repeat the whole process and do this right hand rule, then this right hand rule, but you don't have to because we have Newton's third law, which is still true even in magnetism. So if this is pulling, wire 1 pulls 2 to the left, 2 pulls 1 to the right with the same number of newtons. So that gives us the answer with minimal effort. Well, obviously, these are attracting, this is going to be repelling, right? This kind of makes sense. But let's practice our right-hand rules. So once again, maybe what we'll do is do it the other way. Let's figure out the force on this one. So at this location, I'm going to create a pause, figure out the direction of the magnetic field caused by wire 2 at location of wire 1. So go ahead and do that now. All right, so your 2 choices are either towards the top of the screen or toward the bottom of the screen. The radius vector, so we got to go 90 degrees from that. We use our right hand rule, and we put our thumb in the direction of the current, and our 4 fingers will show us the direction the magnetic field goes around the wire. So at this point, it's going up. So here's B caused by wire 2. So B2. Now, the force caused by that magnetic field on this current, you need the other right-hand rule. So let me create a pause to allow you to practice that. All right, here's what you should have done. The current is coming out of the board, so I'm going to put my index finger in the direction of the current like this, right? Now these 3 fingers, I have to rotate my wrist so that these 3 fingers align with the magnetic field. So I've got to turn like this, and I see that my thumb points to the left of the screen. In other words, this wire is pushed that way. So this is F on wire 1. And so by Newton's third law, oops, I should have done that one red, but that's okay. This force has to be the opposite, the same number of newtons. That's F on wire 2. So there it is, the analysis of the right-hand rule. Let's now figure out the magnitude. Remember, F equals ILB sine theta. So let's find the force on wire 2. In either case, it doesn't matter. So that'll be the current in wire 2, the length of wire 2, the magnetic field from wire 1, times the angle between the magnetic field and the current. Well, these stay, but the magnetic field from wire 1, that's mu 0 I over 2 pi r. Well, if they're a distance d apart, I'm going to use 2 pi d on the bottom. So there's the magnetic field from wire 1. And the angle between the magnetic field and the current, if you look here, here's the magnetic field, the current's coming right out of the board. That's 90 degrees from each other. This one or that one, same 90 degrees. So that just becomes 1. And then I just put everything together. And I drop the L2 because usually in these cases, the 2 wires are the same length. But the key condition is that the length of the wires has to be much longer than how far apart they are for this to be true. Otherwise, we can't use this formula for magnetic field. So there it is. Let me create a pause to allow you to copy this down. All right, so that's magnetic force on a current carrying wire. We use ILB sine theta to figure out the magnitude, and the same right-hand rule that we already practiced for charges moving, but this time, instead of velocity, current. This is still magnetic field, that's still force. Okay, so that is magnitude and direction. All right, so I hope you enjoyed the video. I hope you enjoyed the demonstrations with the electric motor. I'll see you in the next physics video.